start that I think we have 16, so that's well enough. Okay, everybody, I welcome you all to the final seminar for this term. So it's going to be Ehud Meir who's speaking, obviously virtually, from the University of Aberdeen, who will speak about interpolations of monoidal categories and algebraic structures by invariant theory. So please, Ehud.
Thank you very much. Thanks for the invitation. So, as the title suggests, I will tell you how to use monoidal categories and interpolations to study algebraic how to use invariant theory to study algebraic structures and monoidal categories. Let's begin. So, in this talk, I took it from, and I forgot to change it, sorry. So I will tell you about invariant theory for algebraic structures. I will tell you about the universal ring of invariants and constructions of a symmetric monoidal category out of characters of this universal ring of invariants. Then I will show you some examples. Most of them are well known and were constructed by Deligne and Knupp, but there are a few new ones as well. Okay, so first let's fix a field K that is algebraically closed and of characteristic 0. And our framework here will be that of finite dimensional algebraic structures over K. And as examples, you can take just algebras, associative or Lie algebras, Hopf algebras, comodular algebras, Frobenius algebras, anything that basically is given by some linear map between tensor powers. So by such structures, we really think of them as a vector space A, together with some finite set of structured tensors, xi, that goes from A tensor qi to A tensor pi. Think, for example, about multiplication, or in a Hopf algebra, co-multiplication that goes from A to A tensor A, and so on and so forth. Unit will be an element from in A, which is just a map from K to A. And K we can also think of as A tensor 0. Okay, so these numbers that we have here, pi and qi, we will just call the type of the algebraic structure that we have. And we will write symbolically the structure tensors like this. So this is M, indicating that it has two input strings. It goes from A tensor A to A. And here we have delta going from A to A tensor A. So it has one input string and two output strings. And we always think of this morphism as going from the bottom up. Okay, so for example, a unital algebra has type 1, 2, 1, 0, because we have one multiplication going from 2 to 1 and one unit going from 0 to 1. And okay, the structural tensors usually satisfy some sort of axioms, and these axioms can be written using diagrams. So here is, as an example, here is associativity. Okay, so this is when we want to say that xy times z is equal to x times yz, is just to say that these two diagrams are equal to each other. Okay, so here's a question, a naive one, but still somewhat relevant. Can we classify algebraic structures of a specific type, or maybe only those who satisfy some set of axioms? So in general, this is very difficult, and I guess I see at least one person in the audience who is very familiar with how difficult it is for some finite dimensional Hopf algebras. And what we will do here is I will try to explain you how to approach this problem using geometric invariant theory, which is some tool coming from algebraic geometry. Okay, so what's the idea with invariance? So the idea is that we, for every object, or for every, to be precise, isomorphism type of object, we can assign some numbers. And then different structures, non-isomorphic structure, hopefully will have different invariants, and these invariants will enable us to distinguish them. So the first invariant that we have is just the invariant that we have just as vector space, and this is the dimension of the algebraic structure. Is there any question? No, fixed. Okay, so in other words, let's say it like this. If we have two algebras, A1 and A2 of dimensions D1 and D2, and the dimensions are not equal, then we know for sure that A1 is not isomorphic to A2. And this is because they are not even isomorphic as vector spaces, then, so let alone not as algebras or as any kind of structure they have. So let's now fix the dimension D. Let's assume this dimension is finite. And then we can ask something more specific. Okay, can we classify algebraic structures of type AQI of dimension D? Or let's now ask a bit of a refined question to explain how we get into algebraic geometry from this. So we can ask, what is an algebra of dimension D? So here's an answer. We need to choose, and notice that I emphasize the word choose here, a basis E1 up to ED for the algebra, and then the multiplication is just given by the structure constants, by the cube number, MIGK. How does it look like? So M of EI tensor EJ, two of these basis vectors, is equal to the sum of MIGK times EK. Okay, so in this way, we can think of the multiplication instead of as a linear map. We just think of it as a collection of numbers or as a point in the affine space A to the D cube. So this is nothing new, right? I mean, in linear algebra, one of the first things that you do is to say, let's fix a basis. Then a linear transformation for me now is just a collection of numbers, is a matrix. In this case, it's not D squared but D cubed because we go from A tensor A to A. But still, the idea is the same. Fix a basis, then it's just a bunch of numbers. Then the good thing is that when we want to specify a property like an axiom such as associativity or commutativity, then we still have we can still describe it by a set of polynomial equations. So we are still in the realm of algebraic geometry. So here's an example of associativity. Associativity is just given by this quadratic set of quadratic polynomials for every I, j, k, and b. This sum should be equal to this sum. The idea is that you just try to multiply EI tensor EJ tensor EK and see what happens, and you compare the coefficients, and this is what you get. Commutativity is easier because it just involves like one instance of the multiplication, and then we just get a linear equation, just MIJK is equal to MJIK. And we can apply exactly the same principle to much more complicated algebraic structures like Hopf algebras, Lie algebras, Frobenius algebras, braided vector spaces, algebras with a group grading, and so on and so forth. So everything that you can write really as a finite dimensional vector space together with some structure, you can put in this field. Okay, so in this way, we translate everything to algebraic geometry, right? Because we have a set of, we started with this affine space, A to the D cube, and then we say, if we care about specific axioms, then these are just closed, Zariski closed subsets. Now, still a serious problem is that the structural constants are not unique. Remember, I told you that you need to choose a particular basis in order to get the structural constants. And let's rephrase this maybe. So in the algebra example before, we have A to the D cube, and we have Y subset, which contains all the associative multiplications. This was Zariski closed. And then the additional piece of data that we have is that we have an action of the general linear group, GLD of K, on A to the D cube that restricts to Y. And what we really want to understand is the set of orbits, Y modulo GLD of K. Why do we want that? Well, the idea is that because the action is given by a change of basis, it will happen, sorry, that orbits just correspond, GLDK orbits just correspond to isomorphism types. And the reason that the action of GLDK on a D cube restricts to Y is just that if you take one associative multiplication, you do a change of basis, it will still be associative also when you write it in a different basis, right? So you won't move outside of Y by acting with GLD of K. And okay, to study this kind of quotient, this Y modulo GLD of K, this is something that we know how to use, how to do from invariant theory, or at least invariant theory gives us some tools to study this type of quotient. Okay, so how exactly does it go? So we fix a type, this just collection of integers, pi and qi, just saying how many boxes we have and how many, to each box, how many inputs and outputs it has. And we write UD for the affine space made of the structural constants for structures of dimension D of this type. Okay, so previously it was just a D cube, if we don't consider any kind of axioms, and in general it can be a affine space from higher dimension. And we have an action of GLDK on UD, again given by a change of basis. Here's a theorem of Manfrotto that pretty much summarizes what we will use from geometric invariant theory. He showed that there is an affine variety XD such that the invariant ring KUD to the GLD is exactly the coordinate ring of XD. And the points in XD, this affine variety, are in one-to-one correspondence, not with all the GLD orbits in UD, but only with the closed GLD orbits in UD. Okay, so in particular, the invariants form a complete set of invariants for closed orbits, which mean that if we have 2 points in different closed orbits, there will be an invariant that will separate them, that will not be equal on this, will not have the same value on both of them. So why do the invariants appear here? Just the intuitive explanation is, think about it like this: if we really have this kind of map from UD onto UD modulo GLD, then function on this should be constant on orbits, right? And constant on orbits just say that they are invariant and that there are functions that are invariant under the action of GLD. So that's the reason that we actually get invariants to begin with. Okay. Any questions before continue? Okay, so if not, let's start with seeing some examples of invariant theory. So the first example that you have seen, and that was a long time ago, was when talking about congruence of triangles. And in this case, we ask, when does it happen that two triangles in the plane are congruent to one another? Okay, so think about like this: you have delta 1, A prime, B prime, C prime, and delta 2, A, B, C. So how is this a geometric invariant theory problem? So think about it like this: what does it mean that two triangles are congruent? It means that you can get from one to the other by translating, rotating, and then maybe reflecting. Okay, but this is exactly to say that you have X here, the set of all triangles in the plane, and you have the group gamma, which is the semi-direct product of O2 with R2. The R2 stands for the translation and the O2 for rotation and reflection. And we want to understand the orbits of gamma in X, because these are exactly the congruence classes of triangles. And we actually do have some invariant theory kind of answer to this coming from Euclidean geometry. We have the side-side-side theorem that says that delta 1 is congruent to delta 2 if and only if ABC is equal to A prime, B prime, C prime. In other words, if the edges are the same, if we have the same side lengths. Okay, so you can just think of the side lengths as some sort of as scalars that are invariant under the action of gamma, and they give complete set of invariants in the sense that they determine what the triangle is. Of course, this is not completely accurate because we talk here about a non-algebraically closed field and so on. This is R and not C, but nevertheless, it captures the essence of this. Now, let's go to another problem about conjugation of matrices, and this is what I mentioned before. So one of the main things that we do when we teach linear algebra is that we want to classify all linear endomorphisms of vector space of dimension D. Okay, so again, only up to conjugation by GLD of K, because this just means that it's the same transformation, only in different bases. In other words, we want to study the quotient of MD of K modulo GLD of K. Okay, so now the ring of invariants here is known to be, in this case, K of MD of K. This is polynomial ring in D square variables. And when we take invariants, we just get polynomials in D variables, C1 up to CD, where C1 is the trace, CD is the determinant, and everything else are the coefficients of the characteristic polynomial of the linear transformation T. Okay, so another way that we can write this polynomial algebra is also as polynomials not in C1 up to CD, but in trace C, trace T square up to trace of T to the D. Okay, so before I continue, let me just say, so this is basically the usual thing that we have whenever we have a linear endomorphism of K to the D. The first thing that we ask is, what are the eigenvalues? And to ask it in a more symmetric way, we can ask, what is the characteristic polynomial of this? Because this really tells us kind of what the linear transformation is. However, we have one drawback why geometric invariant theory doesn't fully work here, is that the orbits are not closed, and we cannot distinguish, for example, these two orbits, the zero matrix and the nilpotent 2 by 2 matrix, nilpotent non-zero matrix. And this is because the orbit of 0, 1, 0, 0 contains all the matrices of the form 0x, 0, 0 for x that is not 0. But then when we take the limit, when x goes to 0, then we also get this 0 matrix on the boundary. So it looks, illustratively, it looks something like this. We have this green orbit on the boundary of the blue orbit. Okay, so just by continuity, we know that invariant polynomials cannot distinguish these two, and we really do know that okay, if we look at trace and determinant of this matrix 0, 1, 0, 0, they are both 0, and this is the same as trace and determinant of the 0 matrix. So just scalar invariants are not enough to distinguish them, but still they help us to study quite a lot, right? They are quite useful in understanding at least the spectrum of the linear operator. Okay. So we already see that non-closed orbits are going to give us a bit of a hard time here. And let's see how they can give us a lot of hard time if we are just in a situation of, let's say, just an associative algebra. So if we try to play the same thing just for associative algebra, then it won't really work. And this is because the 0 multiplication will be in the closure of every other orbit. Okay, so if we just rescale our basis elements by lambda, then we rescale, because here we have two lambda EI and lambda EJ, and here only one lambda EK, then we actually rescale our structure constants by lambda. And then by letting lambda approach 0, we just get that the identically 0 multiplication is on the boundary of the orbit of M, no matter what M is. And as a result, the ring of invariance is really not interesting. It's just a ground field, and it gives us no information. We cannot say that this invariant tells us something. We don't have any non-trivial invariants. However, and this is the point, that the more complicated algebraic structure we have at hand, the more invariants we get. And I started this business by doing Hopf algebras, and they are quite rich in the sense that they have both multiplication and co-multiplication, and unit and co-unit, and also the antipodes. So a situation like what we have before with only associative multiplication do not happen. So I would like to tell you how we get invariance, and for this I will start by telling you how we get what I call constructible maps. And the idea is like this, is that you can just take the original maps you started with, like M and delta. It can be Hopf algebra or Frobenius algebra or anything else, and just combine them together. Like, for example, here we see that we mix the two inputs of M, and here the output of delta goes to this input of M, and so on. And we get maps, in this case, from A tensor A tensor A to A tensor A. Okay, so why do we call it constructible? How is it constructed? So first, it's constructed by taking tensor products of maps. Then we can apply tensor permutations like we have done here. And finally, we can connect input and output strings. And this corresponds to applying the evaluation on A star tensor A. Okay, I do not assume here necessarily that A is self-dual, that A has an inner product, even though in most examples I will give you, it is the case that A has an inner product. Okay, so of particular importance, we get the closed diagrams where both P and Q are 0, 0, and they represent linear maps just from the ground field K, which is A tensor 0, to K, which is again A tensor 0. And these are just scalars. And here's an example representing trace of delta composed with M. Okay, so we see here we can draw this as a diagram. We don't have any free input strings and no free output strings. This is just one complete picture in a sense. And it really represents a number, right? Because whenever you have some map from A to A tensor A called delta, a map from A tensor A to A called M, you can take the composition of these two, calculate the trace, and you will get a number. And in this way, you really get, every closed diagram really gives us a scalar invariant. Okay, so what can we do here? So we write con PQ for the free vector space spanned by the diagrams of constructible maps from A tensor Q to A tensor P. And then if we consider all the constructible maps for all P and Q, it's equipped with some useful structure. We have this kind of multiplication given just by putting diagrams one next to the other, from con AB tensor con CD to con A plus C B plus D. We have a pairing, which is given by taking trace, and sorry, by taking composition of maps and taking trace. So here's the example when P and Q is 3 and 2. If we have one diagram with 2 input strings and 3 output strings, and one with 2 output and 3 input strings, what we can do is we can connect the input strings here to the output strings here, and the input strings here to the output strings here, and we can get a closed diagram. So in this way, we get a pairing from con PQ tensor con QP to con 0, 0. And in particular, when we look at con 0, 0, this is an algebra because, as we said, there is a product given just by putting diagrams right one next to the other, which does correspond to, when you think about evaluating them on particular structure, this just corresponds really to taking multiplication. Okay, so what we get here is actually a polynomial algebra over the set of closed connected diagrams. And it's important here connected because then every diagram that is not connected, you can just write as the product of the diagrams coming from the connected components. And moreover, what happens is that if we have any algebraic structure of type PIQI, then evaluation gives us a character from this algebra generated by the diagrams, which we call the character of invariance of this thing, right? Because elements here in KXOG, they are just linear combinations of diagrams, and every diagram, because we can assign to every diagram, we can assign a numerical value, just by evaluating it at this particular a comma yi. Okay, so we call this character that we get here, and by character I really mean ring homomorphism. We call this the character of invariance of the structure AYI. Okay, that's on the one hand. On the other hand, I still need to tell you how does this relate to the algebra of invariance we mentioned before, this KUD to the GLD. So here's the thing, we have a natural map from KXOG to KUD to the GLD because every diagram we can think of as an invariant. And notice that we can think of this as invariance for structures of dimension D or D+1 or 2D or any dimension. So we do have a map from KXOG to KUD to the GLDK, no matter what D is. D can be very large or very small. And here's the theorem is that this natural map that we have is in fact surjective. So all the invariants that we get that are GLD invariants in UD, they all come from this kind of diagrams that we can draw in this way. And now geometric invariant theory, if we look at what it actually tells us, it tells us that the orbit of AYI, or in other words, the isomorphism type of the structure that we get. So let me rephrase myself. It says that if we know that the orbit of these structures, AYI, is closed in UD, then the character of invariance that we have, it will be the same as knowing the character on this algebra, on KUD to the GLD, and then it is enough to recover the isomorphism type of this thing. Okay, so allegedly we know that the character contains enough information to recover what we started for, but then we can ask how. And the idea is that we construct a certain category to do it. And I would like to ask at this point if there are any questions before I continue to tell you how.
Yes, I have a question, actually.
Yes.
This is more a curiosity than a question. Do you have a description of constructible maps for this category of constructible maps for A-infinity algebras? Because I'm interested in that because for various reasons, and because basically you can in that framework you build the n-ary operation starting from the n-1. So I don't know, maybe it's a nice category for this reason, maybe not.
So I think that, okay, so I guess one thing is, if I understand correctly, I don't know enough about the infinity algebras, but I think, first of all, you have infinitely many operations there, right?
Yeah, it's right.
And do you have like you don't have usually a finite dimensional vector space, right? It's an infinite dimensional one, or it's graded one.
It can be also a finite dimensional space. But yeah, my point here was that somehow you construct the n-ary operations, so the operations that take n guys and spit out, let's say, one element of the algebra, starting from the previous one. So basically, you have a recursive way of giving these operations. So that's why I was thinking that maybe a description of this operation in terms of constructive maps might be nice.
Yeah, so I mean, I think that most of what I will tell you here can be done for infinity algebras. Some of the theorems will not work because I really count on having only finitely many structural tensors, and then you can kind of think of the A infinity lemmas A infinity algebra as the limit, where you take more and more structural tensors, but only finitely many at any given point.
Okay.
And then I think it should work. I mean, especially that. Okay, so do you know examples of automorphism groups of infinity algebras?
No, unfortunately, no. I just, I only started to be interested in infinity algebras some years ago, but then I left. So yeah, unfortunately, I don't know any deeper the theory of these guys. Yeah, sorry.
Okay, I mean, I will try to add some details after I will give the construction of the category. But
okay,
yeah,
thank you.
Yep. Any other questions? Not then. Okay, so let's continue. We have the character of invariant, and we want to see how we recover the original structure we started with, our algebra, Hopf algebra, vector space with an endomorphism, anything that it might be. So we do the following. We construct a category called C chi, and we do it like this. First, we just write chi for this character coming from A, Y, I. And then we say, okay, so recall that we always have this kind of pairing from formal maps from A tensor Q to A tensor P with formal maps from A tensor P to A tensor Q by taking composition and trace. And this gives us an element in KXO. And we can compose this pairing with chi, and then we say that F is chi negligible if it's in the radical of this thing. Okay, of con PQ tensor con QP going to KXO going to K. In other words, if it's perpendicular to all of con QP under this pairing. Now what we do is that we construct a symmetric monoidal category in the following way. So for objects, we just take all objects of the form WAB, which are formally tensor products of W tensor W A times with W dual B times. So for us, we can also say that the objects are just pairs A, B, where A and B are in N at this point. The morphisms are all the constructible morphisms, modulo chi negligible morphisms. We have to be a bit careful here. I mean, we know what will be all the maps from W tensor Q to W tensor P, but we can also describe from WAB to WCD by using the usual adjunction of the dual W star here. And we then close the category under direct sums and direct summands. So this is something that we can do quite formally. I mean, direct sums, we just say that, okay, formally we have a direct sum and we know how to home into and out of a direct sum of things. And direct summand as well, we just add kernels and co-kernels only of projections. This is kind of a standard procedure known as taking the Cherubian envelope. Okay, so we form this bunch of categories C chi, and what kind of categories do we get here? So here's a theorem. So let's assume again that we start with an algebraic structure, which is of dimension D and has a closed GLD orbit and the character of invariant chi. So when we construct this category C chi, what we actually get is the representation category of the automorphism group of this structure, AYI. Okay, so what do I mean by auth of AYI? So an automorphism of this thing is just a linear isomorphism from A to A that commutes with all the structure tensors. So for example, for multiplication, this is just the usual definition of homomorphism of algebras, right? That G of X times G of Y is equal to G of XY. It commutes with M. And then the idea of proof is to use the theory of the linear symmetric monoidal category, specifically on Tanakian one. We can use what Relin did in order to show that there is a fiber functor from Ck to Vec, and then use Tanaka duality to show that this is really rep of some group G. And then we show that the group G is really this automorphism group, and this G is really reconstructed as the automorphism group of this fiber functor. Okay, so here is one thing that this implies. It implies that if we take Aij and we take the OT A invariant, OT A mean here always OT A with respect to the structure tensor, this Yi, then this is spanned by constructible elements. So this is kind of a result that it's not so hard to prove in one direction that all constructible maps are invariant under OT AYI. So here's an example with the previous constructible map we had before, that if we have 3 times G in the entrance, we can just use the fact that G commutes with M and with delta to show that this is in fact equal to this diagram with G's in the outbound. Okay, so however, what the last theorem tells us is that also the opposite is true, and that every OT A, YI equivariant map is spanned by constructible map. So everything that commutes with the automorphism group can be written as a linear combination of such diagrams. Okay, moreover, we can get any category of the form rep G, where G is a reductive algebraic group this way. And you might ask, why do we need reductive? Well, reductive groups are those for which rep G is semi-simple, and the only categories that we will get are going to be semi-simple categories in this situation. Moreover, whenever we have a closed orbit, then automatically if we have a structure with a closed orbit, then we can think of the automorphism group as kind of the stabilizer in GLD. And it is known that in this case, the stabilizer must be a reductive group. Okay, so now notice that the construction of the category Ck doesn't really depend on the fact that Chi comes from a real structure, like from a structure in vector space, in vector spaces, right? We could have just taken any other character and just apply the same construction of dividing out the chi-negligible morphisms and then take direct sums, direct summands, and so on. And we can do it, okay, with any other character, and we can ask what kind of characters do we get in this way. Okay, so here's the definition. So K-linear rigid symmetric monoidal category is called K-good if it's abelian and has finite dimensional Hom space. I would like to give some background here. So K-linear means Hom spaces are K vector spaces. Rigid, I mean that we have dualities. So every object X has another object X dual such that we have evaluation and co-evaluation that satisfy some usual axioms. And we say that a character is called good if it satisfies the following 2 conditions. Yes, first of all, we want that the radical of this pairing should have finite codimension. This is just because we want to have finite dimensional Hom spaces. And the other thing that we require is that if we have an nilpotent endomorphism in Ck, then it should happen that the trace of T is 0. And this is property that should be satisfied if we want to have an abelian category. Okay, so we give here 2 different definitions, one of about categories, one about characters. And this is the connection between them. So let's say we have some character. The following conditions are then equivalent. One is that the character Chi is a good character. And the other is that the character Chi is the character of invariance of an algebraic structure in some K good category D, and that the category Ck itself is K good and semi-simple. So in other words, the good characters, those that satisfy the 2 conditions in the previous slide, are exactly the categories that come from structures in nice enough categories. Okay, so now we can ask something quite reasonable. How can we get more good characters? Because so far we just say, okay, if I have an algebra inside Vec, then I get a character. But as we all know, getting algebras or getting concrete examples, I mean, usually they can be quite scarce, right? So here's what we can do. So we give the following definition: a 1-parameter family is a collection of characters such that if we fix the closed connected diagram D, it holds that the value of chi-t of d is a polynomial in T. Okay, so it really changes polynomially nicely algebraically. Now, here's what we can do. Let's assume that we have a one-parameter family of character, and let's assume that we have a countable set, S1, S2, and so on, such that chi Si is a good character for every I. Like usually these will be the structures coming from, characters coming from structures in VEC. Then under some mild assumptions that I will not tell you exactly what they are here, chi-t is good for every t and k, or for almost every t and k, in some even milder assumptions. So how does this look like? Here's an illustration. So here you see the field k, and here you see the specific values S1, S2, S3, S4, S5, and so on. Unfortunately, I couldn't really write down countably many numbers on this field, but the idea is that if we know that something works for all of this, and it works for the entire field. And this will be quite useful for us to get more examples. Okay, so I would like to show you now what kind of other categories I get. And these categories are in fact, they are not really, the idea is not really new. And many of the examples that we get here were already constructed by Deligny before, and some other people as well, as I will just say. So here's the construction of the original construction of Deligny. He showed, he constructed categories which he called rep st, where t is not an integer. So the idea is that we can consider the symmetric group as n, and then the representation category is rep as n. And Deligny showed that they admit a uniform description. So he gave a list of objects, x1, x2, and so on, that makes sense in rep as n for every n. Xm is just the linear span of injective maps from m to n. So notice that for if I fix n, then for very big m, this is 0. But still, this kind of definition of an Sn representation makes sense for every n. Then he also showed that the home spaces, home Sn from xi to xj, they can be described uniformly independently of n, and that the coefficients of the compositions are polynomials in n. And this is quite important because once we have polynomials in n, we can also consider polynomials in t. And this way he defined abstractly the categories rep as t. He just replaced n in t, but took the same objects and same morphisms. And he also interpolated other families of symmetric monoidal categories, such as rep of GLT-K, rep of OT-K, and rep of SP to T-K. I think that I had some private communications with him, and it seems that he knows he knew at the time how to interpolate some other families as well, like representations of GLN-FQ or GLT-FQ, where FQ is a finite field, but he didn't publish it. Okay, so these categories, unlike the case of rep Sn or rep GLN and so on, they admit a fiber functor only when t is equal to n. And when t is not equal to n, you get these kind of categories that they look very much like a rep of something, only that objects grow too quickly. So they aren't really. Okay, so let's see how we can use the categories we mentioned here to get the same examples Deligny constructed and a few more. Okay, so let's just begin with considering the empty structure, in which case we just have 0 structural tensors. So in this case, the algebra of invariant is just polynomials and the polynomial algebra in a single variable d, where d is the dimension. Okay, or we can think of it drawing a diagram. D is the trace of the identity map. And it also holds that con pp is just the group algebra over kd of the symmetric group on p elements, and con pq is 0 for p not equal to q. And then we write chi-t for the character given by chi-t of d equal to t. And then for n in n, it holds that chi-n is the character of invariance of the vector space k to the n with no extra structure. So we have that c chi-n is rep gln. And then the categories ck-t, which are also good categories, as we mentioned before, they are rep GLT. And one consequence that we have from this is that we recover Chauval duality. So since all the invariants are constructible, we get here that the following description, at least of a spanning set for home GLN between different representations of GLN. So the home between Kn tensor A and Kn tensor B is 0 if A is not equal to B, and it is spanned by L sigma if A is equal to B. What do I mean by L sigma? I just mean like take, let's say you have W tensor W, tensor W, tensor W, tensor W 5 times, and just somehow mix the 5 tensors of W, and you get a GLW equivalent map. And what sure-val duality says, and what we recover here, is that all the GLD equivalent map, they arise in this way, as linear combinations of these things. Here is something slightly more complicated. Let's consider a vector space with a non-degenerate symmetric pairing, C from W tensor W to K. So how do we record the fact that it's non-degenerate? Well, we want to say it somehow using axioms. And the non-degeneracy is equivalent to having a copairing, right? And the copairing is just a map D going from K to W tensor W, such that this holds. So when we enter one hand of D to one of the legs of C, we just get the identity of W. Okay, so now we consider the theory containing the above axiom and the symmetric axiom for C, saying that C of X tensor Y is equal to C of Y tensor X, basically. And the resulting algebra that we get is, okay, not KXOG, but here we have KXOG modulo the ideal generated by the ideal that promises us that these two axioms will hold. Again, we get something that is isomorphic to KD. And using the same family KT as before, we just get that KT is good character for all T and K. And if we take T is equal to N, we get the representation category of ON. That is the algebraic group of all A such that A times A transpose is 1. Okay, and so these categories we get here, they interpolate the categories rep ON. And in particular, using, again, the fact that all the invariants are constructible, we get this kind of description for the home spaces. Okay, so home ON Kn tensor A, comma K, it has the following description. It's 0 when A is odd. When A is equal to 2B, then this is just given by taking C tensor C B times and apply some permutation in the entries, like this. Okay, so here you see, for example, the constructible maps that I wrote here. Another thing is that a similar construction works also for the family rep of SPT of the symplectic vector spaces. Okay. And so this is an example of one constructible morphism, and the idea is that we can actually get all constructible morphisms in this way, just as linear map combination of this. I chose to tell you here about home between Kn tensor A and K, but you can also get all home Kn tensor A, Kn tensor B in this way, just by using the duality and using the fact that K to the N is dual to itself in this setting. Okay, questions? If not, so I will continue with some other examples. So the most, I guess, famous and celebrated example is the one of rep ST. And the idea here is that we, unlike in the construction of the Lin that actually understood something about the representation category of Sn, we really don't have to understand here much. We just need to know that Sn is the automorphism group of a certain object, of a certain algebraic structure. And what will be this algebraic structure? Well, we can consider algebraic structures that are made of 3 tensors, M, C, and U. M is multiplication, U is unit, so we get an associative and commutative multiplication, together with C, which is the separability idempotent. It's an element in A tensor A. So they should satisfy the following theory T of commutative separable algebra, that is associativity, commutativity, U is a unit, and C is a separability idempotent. Okay, and again, direct calculation shows that the resulting algebra of invariants after dividing out by the ideal IT gives us, again, a polynomial ring in one variable T, and this gives us, again, a one parameter family. And for T is equal to N, chi N is the character of invariance of the commutative separable algebra A is equal to K to the N. So in this case, multiplication is just a pointwise multiplication in the coordinates. U will be just 1, 1, 1, 1, 1. And C will just be the sum of EI tensor EI. And what we have here is that Ort A is Sn, and we thus get that C chi N is rep Sn, and C chi T is therefore rep St. So this gives a slightly different construction, although not very different, but slightly different construction to the categories rep_t of the line. He also proved that these categories, at least when t is not an integer, satisfies some universal property for commutative separable algebras. Okay, so the mild condition that I mentioned before, they met here, and really rep_t gives us a collection of good categories. Okay, so here is another example that was recently constructed by Chovanov, Ostrich, and Kononov. And this is the example of commutative Frobenius algebras, which is very similar to the previous one, only that there is some kind of extra structure. So every commutative separable algebra is also a Frobenius algebra, but not vice versa. The Frobenius structure can be more complicated. So such a structure is given by the following tensors. We have m, delta, u, and epsilon. And we use the fact that commutative Frobenius algebras are equivalent, in fact, to two-dimensional oriented topological quantum field theories, or Tqft's. And here is the kind of dictionary to pass between them. M multiplication is just a pair of pens in this direction. U and epsilon are half spheres. C, which I didn't write here, is this kind of shape. So cylinder that goes like this. Delta is a pair of pens in the other direction, and the identity of W is simply a cylinder. And then what happens is that closed diagrams are then just equivalent to two-dimensional closed oriented manifolds, right? Because you connect them together, and to say that something is a closed diagram just means you don't get any circles, any S1s on the boundary. And these are classified, these two-dimensional closed oriented manifolds, they're classified by their genus. And then we get an isomorphism here between kx og mod it to actually now a polynomial in infinitely many variables, d0, d1, d2, and so on, where dg is a closed connected diagram that corresponds to a genus G surface. And the corresponding character is then determined by the numbers alpha G, which is just what happens when we apply chi to dg. Okay, so now we don't have only one number as before, we have infinitely many, countably many. And we can ask, okay, so what are the good characters that we get now? And this is a theorem that was first proved by Chovanov, Ostrich, and Kononov to show that they didn't use the same terminology. They put their paper on the archive a bit before I put mine, but what they showed in this terminology is that the character chi is good if and only if the following condition holds. So if you look at this formal sum alpha g times x to the g, then this should be a rational function, and moreover, it should be a rational function of a specific form, which should be in the span of x and 1/1 minus lambda x. Okay, and the resulting category C chi is what Chovanov, Ostrich, and Kononov called the decob underline alpha in their paper. How much time do I have left? By the way, I cannot hear you. You're on mute.
The convention, I guess, is that 1 hour and a half is an upper bound.
1 hour and a half.
Is an upper bound, definitely an upper bound. But
these are usually about an hour.
Usually about an hour. But if you want to go 10 minutes, it's over.
Okay, yeah, I should have asked it before, I guess. Okay, so yeah, I mean, okay, so in any case, I still have some time, right? Yes. Okay, so another thing that I can then tell you, because I have some time, is some work in progress I'm doing now with Niels Skarkville and Laurent Szegedy. And what we do is that instead of looking at oriented two-dimensional Tqft's, we are looking now at R spin two-dimensional Tqft's. So again, the motivation comes from topological quantum field theory. And a lot of what people do in Tqft's, I mean, also in higher dimension, is to try to understand if there is some algebraic structure that hides here. And then if so, how can we describe it? Can we study it algebraically and so on? And specifically what we were looking at is something called R spin two-dimensional Tqft. And the idea is the following, is that for every R in N, the group SO2 admits an R-fold covering, GR to SO2. And then an R-spin structure on a two-dimensional cobordism. So the objects in Tqft's are basically cobordism. They are, they are the one going from between these circles on the boundary. This is a GR principal bundle over M that reduces to the canonical SO2 principal bundle. So here's a theorem about this kind of R-spin Tqft's. So first, a closed surface of genus G that meets an R-spin structure if and only if G is equal to 1 mod R. So the those yes, and then R plus 1, R plus 2, 2R plus 1, 3R plus 1, and so on. If G is equal to 1, then R-spin structures on sigma 1 are in 1-to-1 correspondence with divisors of R. So here I just mean those. If G is equal to Rk plus 1, then there is a unique R-spin structure on sigma G if R is odd, and 2 R-spin structure on sigma G if R is even. Okay, so then the algebraic structure that corresponds to R-spin two-dimensional Tqft that was developed by Laurent Segati and Walker, and this is called Lambda R for Bennis algebra. It's very similar to the community for Bennis algebra, but it is more complicated, and we should take into account more axioms. Then the scalar invariants that we get are then correspond to closed R-spin surfaces, and we denote the list of invariants that we get here by beta D, where D divides R. So these correspond to possible R-spin structure on sigma 1, and then alpha 1, alpha 2 for everything higher. And this is where R is odd, and if R is even, then we also need to add alpha 1 plus, alpha 1 minus. This corresponds to a surface of genus 1 plus R with the first structure, and then with the second structure, and so on. And this is a theorem that we proved very similar and very much in the spirit of the Khovanov-Oster-Kononov paper, is that if R is odd, then the tuple that we say here corresponds to a good character, if and only if the sum of alpha I xi is in the span of this function, like 1 over 1 minus lambda x, or in other words, it's just going to be a weighted sum of such functions. For R even, the tuple corresponds to a good character if and only if this condition holds for both the alpha I plus and the alpha I minus. And notice that we don't really need any specific condition on these finitely many numbers beta D. They will always give us some good category and some good character, and by that also this kind of category, which is abelian, semi-simple, and with finite dimensional home spaces. One last example I would like to tell you about, a bit in a different spirit, is what happens when we take modules over discrete valuation rings. So think, for example, on something like the p-adic numbers, where we have a uniformizer pi and a finite residue field like Z mod P or FQ. And we can consider the finite O modules, and they are all going to be of the form, and this we know by the theorem of modules over PID, finitely generated modules over PID. All the finite O modules will look like something like O mod pi to the A1, direct sum O mod pi to the R to the AR for some R. Okay, so think, for example, if we talk here about finite modules over the p-adic numbers, you will get Z mod P to some power plus Z mod P squared to some other power A2, plus Z mod P to the R to power AR for some R. Okay, so this is an algebraic structure, but we need to explain how we translate it into an algebraic structure of the form that we were considering here, like a vector space with some tensors and so on. So what we can do is we can take the linear span of M. We take A is equal to Km, so span of UM. And this is a Hopf algebra because it's the group algebra of something. And in addition, it's also equipped with a collection of Hopf algebra endomorphisms, the x going from A to A for x in O mod pi to the R. Okay, so we fix the R for now. We must fix it, otherwise we won't get something finite. And once we fix the R, we can describe it in this way. And the tensors are given by M is just multiplication. This is just given by the addition in M. Delta is just the diagonal. Delta of UM is UM tensor UM. The antipode is given by taking the inverse in M. Epsilon of UM is always 1. The unit is U0. It's the unit element. And the X of UM is UXM. So we just, instead of thinking of multiplication as going from M to M, we think of it as going from Km to Km. Okay. And now here's what happened is that if Chi is the character of invariance of A, of this kind of Km, then for every closed connected diagram, then we can show that it's going to be this kind of invariance. So it's going to be q to the a1 times c1 plus a2 to the c2 plus ta 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 plus ar to the cr for some ci in n. So in other words, for every diagram D, there are ci's such that this equality holds. And then it just depends on on these ci's and on the q to the a1 and so on. And now what we do is that we write chi q to the a1 up to q to the ar. We call this chi. And this set of characters we can interpolate for an r-dimensional family, because instead of q to the a1 really being an integer power of q, we can just take it to be something else. We can take it to be any complex number or any element in K. Okay, so for T1 up to Tr in K, we just define chi T1 up to Tr of D is equal to T1 to the C1 up to Tr to the Cr, which is exactly what we had here. I mean, that is, if we write chi of q to the a1 up to q to the ar, we will just get what we started with. And then what happens is that, again, for every t1 up to tr such that all the ti's are different from 0, the character that we get is a good character. So we get very large collection of categories that are kind of interpolating the representation categories of the automorphism groups of such modules. And this construction generalizes some construction that was given by Knupp of GLT of O mod pi to the R. However, it's more general in the sense that you don't need to consider here only free modules. You can also consider modules that are not free, like for example z mod p plus z mod p square, or z mod p to the a plus z mod p square to the b, and so on, where both a and b are not 0. We also get a kind of description of what will be the home space between Km tensor A and Km tensor B, and we can describe it. I won't go into all the details, but we can describe it using using enumeration over homomorphisms from N to M, and we get at least a spanning set for this home space in this category. Okay, so one last thing I would like to tell you about, because it kind of seems that still all these examples they are kind of limited, but I would like to just claim what I mean when I say that that good characters appear quite abundantly. So let's write P for the set of all closed connected diagrams that we had before, and since Kake's org is the polynomial algebra on P, any character that we have can be considered as a function from P to K, from the set of connected diagram to K. And this is actually all that we have in a homomorphism from a polynomial algebra to the ground field. We just need to say where the generators go to. Alternatively, we can think of every character as an element in the algebra K to the P, the algebra of functions from P to K with pointwise addition and multiplication. Okay, so what does sum and product in K to the P mean for characters? And this is the thing that if we have one object with character chi and another one with character psi, then we can form always the direct sum of the two, and this will have character chi plus psi. And the tensor product we can also form, and this will have character chi times psi, again when addition and multiplication happens now in K to the P. And then by considering this category C chi tensor C psi, we see that the set of good characters is closed under taking sums and products, because then we have one category in which both structures can live simultaneously. But moreover, it is also true that they are closed under multiplication by scalar, which is, it takes more effort to show, but the result of this is that the set of all good characters that we have, they form a K subalgebra of K to the P. And I guess the most extreme example we have seen was the one that appears in the Khovanov-Ostrey-Kononov. We can describe very explicitly the algebra, the kind of algebra that we get there. In some other cases, it is more complicated to say exactly. Okay, so this is all I had to say. So thank you very much for listening.
Okay, thanks, Ehud, for a very nice talk. Surprising connections. So do we have questions from the audience or questions in the chat? So we have a question from that says, what conditions on the type of an algebraic structure P sub I, Q sub I would ensure that con 0, 0 is non-trivial, i.e. is not generated solely by the dimensional invariant?
Yeah, thanks. This is a very good question, and it has surprisingly easy answer. And this is just that, okay, when we look at multiplication, it goes from 2 to 1, so it reduces the number of strings. As long as you have something that reduces the number of string and something that increases the number of string, then you are fine. You will get some invariance in Con 00. So, for example, I mean, the most obvious case is like if you have multiplication and co-multiplication, so you can go from A tensor A to A to A tensor A. Okay, now you can close it and take trace. But whenever you have something that reduces the number and something that increases the numbers, you can just add the right number of boxes to get a closed diagram, and then it will be non-trivial. You will really have something there.
Okay, so there are any other questions?
Sorry, just because I didn't completely understand your last answer. Do you mean that if I just take associative multiplications, that's not enough?
So yeah, if you just take associative multiplication, then you will not manage just by associative multiplication. It's not enough to get invariance out of this. Because I mean, we had the example in the beginning where you can rescale multiplication by lambda, and then you have 0 on the boundary. So the way to resolve this is, I mean, even if you have associative multiplication, if you know, for example, it's separable, you can add separability idempotent, and then it helps you to get something out of this. So to really get invariance. So,
for example, unital multiplications would do.
So unital multiplication, yes, but I mean, if you start with a just unital associative algebra, then I mean you will get invariance. Like so you will get the invariant of trace of multiplying by u and trace of multiplying by u square and so on. But if you know that all of these are the identity, then again you just get dimension. But if, for example, I take an algebra and I add some element, let's say v, that is not the identity, then yes, then all of a sudden you get all kinds of things, like trace of v square, and so on, like trace of or multiplication by v from left and from right and things like that.
Okay, thanks.
Okay, so do we have other questions? If not, then I have a couple of naive questions then. So I mean, if we restrict just to the case of Hopf algebras.
Yes.
So suppose one asks for the simplest, for a finite dimensional Hopf algebra where you have prime dimension. How do you see that everything,
how do you see? So yeah, honestly, I don't think that it will be possible to see it from this perspective. I mean, and this is okay. This is another thing because okay, so I started asking this question really coming from Hopf algebra, and as you say, you then have this kind of very nice theorems about dimension P and dimension PQ classification and so on. And this is what happens when you try to do this for let's say Hopf algebras of dimension P. Then you have on KXOG, you have two types of relation. On the one hand, you have this relation in this ideal IT, which are just encode the Hopf algebra axioms, like multiplication is associative, co-multiplication and multiplication commute by the Hopf axiom, and so on. Then you have the very, very long and difficult relations coming from the dimension. So basically, it will be something like if you have dimension P, then these are relations that will involve P+1 factorial diagrams, which can be quite nasty. And so part of why I went in this direction is to try to avoid this kind of situation, even though, of course, there is the issue that then, okay, then you can ask the question, okay, but how much can this tell you about the original thing you started with, that is Hopf algebras? So here's one thing that I can tell you about Hopf algebras. So maybe let me connect. I have this kind of document camera that will be quite useful for. I guess I need to stop sharing the screen for this. So one thing that you can prove using this is, like, let's say that you have L in H, an integral, and you have lambda in H dual, also an integral in the dual. Then you can just start generating some elements here. For example, you can take L1 tensor L2 tensor L3 tensor L4 times lambda 1 of L5 tensor L lambda 2, and so on. Yeah, and then the idea is that you can show that all of these elements will be invariant under the, I mean, I'm talking here about semi-simple Hopf algebras. And you can show that all these elements will be invariant under the group of Hopf automorphisms of H. But in fact, one thing that you can show is that you generate in this way all the Hopf H invariant endomorphisms. Or, I mean, in this case, for example, it's an element in H tensor H tensor H tensor H tensor H dual. So you can show that you will get all the Hopf H invariants in this way, just by taking all kinds of different combinations of lambda and L, or all different constructible morphisms. And this, for example, was useful to show something like that every Hopf algebra admits only finitely many Hopf orders. That is, there are only finitely many ways to define it over the ring of integers, or over any given ring of algebraic integers. So for pure classification results, I still don't have very direct results, but yeah, I mean, I hope that in the future something will work.
Okay.
But yeah, again, this is what I hope.
So then maybe another naive question,
Yep.
which probably will have more or less the same answer. If you look at Nichols algebras, when they're classifying them, they start to get root data, Lie theoretic type structures coming out. You're not seeing anything at this level yet.
Well, so I mean, one other thing that if you look at Nichols algebras, there is something that you can say. I mean, you can play the same kind of, without the category part, but you can play the same kind of GIT game with Nichols algebras.
Mm-hmm.
And then what happens is that, okay, you can talk, for example, about the set Y of, in this case, not all Nichols algebras, but all, let's say, okay, so let's do it like this. Let's say that I have some nice, not symmetric, but braided monoidal category.
Mm-hmm.
Like Jeter Drinfeld or something or so. And then I look at a given specific object B inside C.
Mm-hmm.
Right, I'll just pass to this camera again. I look at B inside C, and I can take YB to be the set of all connected, co-connected Hopf algebras in C, isomorphic to B. Isomorphic just as an object of C. Yeah, because, okay, think about it. You just say how it splits as an object of the Jeter-Drinfeld category, for example. Then what happens there is that what you can actually show is that the closed orbits are exactly the same as the orbits of Nichols algebras. Of course, then comes the question: how much does it actually help you? So one thing that you can do with this for Nichols algebra is that you can show that if, let's say, you take a V, which is a simple object, and such that B of V is finite dimensional, then you can use this to show that B of V has no deformations. Yeah, that's and then, I mean, you can also use GIT to show some other results, such as that if there are deformations, there are deformations of some very specific form. But yeah, I mean, like I didn't manage to get, okay, I managed to use this kind of thing in order to how does it go? So there are these kind of very, very difficult classification results of finite dimensional Nichols algebras, and mostly like to show that every finite dimensional algebra is a Nichols algebra in the right context of. So this is originally Andruszkiewicz Schneider, but then also Anjono and some other people. And so I managed to use GAT just to cut down some of the calculations they have done, but not to avoid them altogether. There still needs to some very difficult classification and calculations are still needed, but I managed to cut some of them down with this.
Okay, thank you. No, we have more questions either in the chat or.
I might have a question. Can you hear me?
Yep.
Yeah. So sorry. So I maybe would go to the example of the SN or ST. So the SN is the automorphism group of endpoints. So could you pass from just plain endpoints to studying graphs? So in terms of the category, you could do just the thing, just adding one extra morphism that would play the role of adjacency matrix. And
absolutely, yes.
Yeah, I guess you could then find some invariants because there are just finite and many graphs. So this should be possible. And could you then again do this thing from sort of from going from integer number of vertices to this continuous T and define somehow graphs with non-integer number of vertices or something like that?
So in principle, yes, but we have to be very careful how we do it. This is a very good point. And I mean, also, this is a bit where the the mild conditions that I didn't want to tell you come into play. And this is the thing. So if I just, in a very wild way, I just add, let's say, adjacency matrix. So this will be, the adjacency matrix will be an element in A tens away, right? Because it's like for every, and it will be moreover an idempotent in A tens away, because let's assume that every two vertices, they are either connected by an edge or not. There are a few other ways to formulate this, but this is one of them. The thing is that if we want to make sure that, that everything stays finite dimensional, then we need to make sure, for example, that the, how you say that the number of the possible numbers of edges connected to any given vertex should be bounded, right? Because this is something now that because once I have this thing, I can write like let's say I have A, then I will be able to decompose A as the direct sum of AK, such that the AK is the span of all EI, such that the degree of EI is equal to K. Right, let me just add the camera again. Right. Okay, so we get something like this. And if we really want to keep sure that our category has only finite direct sums, that is that A doesn't decompose into the direct sum of infinitely many things, then then we need to make sure that this K is bounded. That's the thing. But once we do this, then definitely we can speak about this kind of graphs. And one of the other categories that we can interpolate. So if we, like, let's say if we have any group G, we can. Okay, so of course we have the category rep G, but we also have the category rep Sn Reef product with G. By the way, do you see it in mirror image or in the reasonable way?
In the right way.
Sure.
Yeah.
In the right way. Okay. Okay. So we have rep of the Reef product of Sn with G, and then we can interpolate this thing also to rep St Reef product with G. whatever that means. So this appears both in the work of Knupp and also in what I have done. And at least there are some families of graphs which you can interpolate this way. So let me think maybe what will be. Okay, I mean, it really boils down to finding, like if you talk about graphs, then it really boils down to finding families that have kind of nice automorphism groups. And then that the home spaces do not, or like let's say the orbits of the elements in the graph, or the orbits of edges, or the orbits of the graph times itself and times, this should all be bounded. That's the main thing.
Okay, yeah, good, thanks.
Welcome.
Okay, so any more questions? No. Okay, it appears not to be the case. So let's thank Ehud again for a very nice talk.
Thank you.
Yep. So I think that's it for this term. I don't know. Karen has the first talk. I guess the first talks in January are still a little bit in flux.
Yeah, so we should resume January 11th, but we're still sorting out just who will speak. So have a happy holidays, all our virtual friends. And we'll see some of the rest of you in person, of course.
Yeah.
In the
Keep an eye
meantime.
on the website, and we'll be updating the talks as soon as anything is finalized.
Yeah.
There were already quite a few names for next term. So